Welcome to today's Explainer. I am so thrilled to have you here. Today, we're basically putting on our detective hats and diving into a pretty fascinating investigation. We are going to master water chemistry by learning exactly how to track down, intercept, and neutralize some incredibly elusive and completely invisible culprits that are probably lurking right in your own backyard.
So, have you ever looked at a local pond, a community stream, or maybe even your own living room aquarium and thought, wait, why is this water suddenly turning thick and green? We've all seen it, right? It's a jarring and honestly pretty frustrating sight. Those massive, suffocating algal blooms, the sudden drops in oxygen, fish gasping at the surface. These aren't just random acts of nature. They are the glowing, flashing red symptoms of a hidden crime scene. And it means we need to launch a serious investigation to figure out exactly what went wrong.
All right, let's meet our two main suspects, nitrate and phosphate. Now, a really vital fact to understand right up front is that these aren't synthetic, lab-created poisons. No, they are entirely natural, biologically essential nutrients. Life literally needs them to exist. But when they enter our water in massive excess, well, that natural, delicate supply chain completely breaks down. They transform from life givers into these invisible villains behind toxic algae, oxygen dead zones, and massive aquatic distress across all types of water systems. To bring these culprits to justice, here is our investigation blueprint. We're going to cover 1. The invisible threat, 2. Testing and tracking, 3. Apprehending nitrogen, 4. Capturing phosphorus, 5. The cleanup crew, and finally, 6. The ongoing patrol. Let's dive in.
Okay, Section 1. The invisible threat and our core strategy.
Before we just start blindly throwing expensive chemicals or fancy filters at a tank of green water, we need a foundational game plan. Think about it like this. You can't just empty a flooded basement with a bucket. You absolutely have to find the source and turn off the faucet first. Our steps here are crystal clear. First, find the origin of the nutrients. Second, track their movement through the environment. And third, apply controls that perfectly match your specific local constraints. It's really about working smart, not just working hard. Which brings us to Section 2, testing and tracking nutrients. Every good detective knows you simply cannot fight what you don't measure. But here's the catch. Raw data isn't enough. Context is everything. Just grabbing a water sample, tossing in a testing chemical, and getting a raw number, that's practically useless on its own. To actually solve this case, you must pair that chemical reading with environmental context. Like, what is the water flow rate right now? What's the temperature? What season is it? This context is exactly how we take a flat, meaningless number and turn it into actionable, tactical intelligence. But when we look at our source material, there is a heavy emphasis on one critical time frame, and that is weeks. A single day's test is just a snapshot. It doesn't tell you the whole story. It's the trending data, analyzed over weeks, that provides the absolute clearest signal of whether your interventions are actually working. Patience is a virtue here, especially when you're dealing with invisible water chemistry.
Moving right along to Section 3, apprehending nitrogen at the source.
With our reliable data securely in hand, it's time to go after suspect number 1, nitrogen. Now, nitrate is incredibly sneaky. It slips into our water through agricultural fertilizer runoff, decaying organic matter, manure, septic leaching, and wastewater. So how do we stop it? We deploy highly specific source control options. We don't just blindly ban fertilizer. We optimize exactly when and how much we use. We aggressively improve soil health so the ground actually absorbs those nutrients instead of just letting them wash away. And this is key. We deploy vegetated buffer strips along water borders. These basically act as a living wall, cutting off nitrogen's supply lines before it even has a chance to reach our precious streams and lakes. But what if the culprit is a massive municipal or industrial wastewater source? Well, you can't just plant a tiny buffer strip and call it a day. For the big jobs, we rely heavily on optimizing microscopic biological processes. We're using nature's own engineered mechanisms here, specifically a 1-2 punch of nitrification followed by denitrification. To make this work, we have to stabilize the incoming water, the influent, to prevent massive, unpredictable nutrient spikes from totally overwhelming our beneficial bacteria. It's a highly delicate balancing act, meticulously controlled by managing oxygen and carbon availability. All right, Section 4. Capturing phosphorus, also known as the stubborn nutrient.
Now we have to completely shift our tactical approach for our second suspect. There are two completely different mentalities we have to adopt as water detectives. As you can see, nitrogen control is largely about biological processing and cutting it off at the source. But phosphorus control, that relies heavily on chemical precipitation and physical traps. Why the stark difference? Because phosphorus loves to grab onto things. It specifically binds tightly to physical particles and sediment in the water. It's a totally different ballgame.
Since we know phosphate binds to sediment, our very first physical trap is simply reducing soil erosion. Keep the dirt out of the water and you keep the phosphorus out. Simple, right? But when industrial or municipal loads are dangerously high, we have to actively force the phosphorus out of the water column. We do this by physically binding the phosphate using specific chemical materials. Think of them as chemical handcuffs, like alum, ferric salts, or lime. And you can't just pick one out of a hat. Your selection completely depends on your existing water chemistry, like pH and alkalinity. This forces the invisible phosphate to clump together into a heavy sludge, which can then settle to the bottom and be removed safely. Which brings us to Section 5, polishing and stormwater management, basically the cleanup crew. Even after all that aggressive frontline interception, we almost always have to deal with legacy sediments and stubborn residual nutrients. And what's amazing is how these universal chemical principles scale up perfectly across entirely different environments. If you have a small living room reef tank, polishing the water means correct feeding, regular water changes, and surface skimming to prevent ammonia spikes. But what if you're managing a massive natural system? You are engineering huge constructed wetlands with very specific water residence times, distinct hydrology, and targeted vegetation to capture those exact same residual nutrients. The scale changes? Absolutely. But the core science, it remains exactly the same. And as any good detective knows, we absolutely cannot forget about the weather. Because so many nutrient problems are rain-driven and transported by storms, we have to actively manage our physical outdoor landscapes. We do this by improving drainage design, reducing bare soil exposure, maintaining incredibly dense vegetative cover, and building physical features like swales and retention ponds. We are basically building massive green obstacle courses to trap sediment before a storm can aggressively wash it downstream. Now, the absolutely crucial takeaway here is that these stormwater systems aren't magic, and they certainly aren't set and forget. I mean, you wouldn't build a massive highway and then just never pave it again, right? You have to treat these vegetative controls and traps like vital living infrastructure. That means rigorous ongoing maintenance. You have to physically remove accumulated sediment from the traps, actively repair erosion in the outlets, and meticulously maintain the health of the plants. That is the only way to ensure they actually remain effective year after year. Finally, we've reached Section 6, iterative tracking and adjusting, the ongoing patrol. Our investigation doesn't just magically end with a single arrest. Professional water management is an ongoing, never-ending patrol. Because things are constantly shifting in nature, you have to iterate quickly based on your ongoing data. Look at this matrix. If you've implemented your controls but nitrate mysteriously remains high, you pivot. You go back and rigorously reevaluate those local fertilizer habits or the wastewater performance. If phosphate is the one still stubbornly high, you pivot again. Verify your physical sediment controls and make sure your chemical treatments are still active. If a specific suspect is evading capture, you use these ongoing tests to tell you exactly where to shine your flashlight next. Ultimately, success really comes down to a comprehensive, step-by-step approach. By meticulously combining testing, relentless source reduction, targeted polishing measures, and then, maybe most importantly, constantly adjusting based on your real-world measured results, you literally transform what looks like chaotic, uncontrollable water chemistry into a highly manageable, incredibly sustainable process. So whether you are trying to manage a massive municipal reservoir, actively cleaning up a local neighborhood stream, or honestly just trying to keep your home's saltwater aquarium thriving, I want to leave you with this final provocative thought. What invisible nutrients are silently shaping the waters right around you? And now that you have the detective's guide, exactly how are you going to track them down? Thank you so much for joining me today on this explainer. Keep observing, keep tracking, and keep learning.